Hello everyone. So in this video we're going to begin with chapter 2, Functions, Equations, and Inequalities. For this chapter, these are the learning objectives. By the end of the chapter, you should be familiar with quadratic functions and different forms in which to express them. Finding characteristics of a parabola, such as the axis of symmetry, x-intercepts, and the vertex. Solving quadratic equations and inequalities, both analytically and graphically. Applying the quadratic formula and the discriminant of a quadratic equation. Then we're going to study rational functions and their graphs and identifying all asymptotes. Solving a variety of equations, both analytically and graphically. So we start with section 2.1, quadratic functions. If a, b, and c are real numbers and a doesn't equal 0, then the function f of x equals ax squared plus bx plus c is a quadratic function. The graph of y equals f of x is called a parabola. And down here we have the quadratic formula with which most of you, I am sure, are familiar. So the solutions to a quadratic equation in the form ax squared plus bx plus c equals 0 are given by this formula, also known as the quadratic formula. In the next slide, you're going to find figure 2.1, where we see a concave up and a concave down parabolas. To the left, we see that if the value of a is positive or greater than 0, then the parabola opens up. We mean this a here. So if this a is positive, the parabola is concave up. Notice that we would have a vertex which would represent the minimum of the parabola or the function and an axis of symmetry. Then if a is less than 0 or negative, we're referring again to this a, the one that multiplies x squared. If that value is negative, then the parabola opens downward or is concave down. Notice that now the vertex would be the maximum of f of x. And of course, we would have an axis of symmetry. On the next slide, you're going to find something that says the graph of f of x equals a times x minus h squared plus k. This is also known as the vertex form of the parabola. From section 1.5, we know that the graph of the equation y equals x plus 3 squared plus 2 can be obtained by translating y equals x squared 3 units to the left and 2 units up. As we are familiar with the shape and position of the graph of y equals x squared, and we know the two translations that transform y equals x squared to y equals x plus 3 squared plus 2, we can sketch the graph of y equals x plus 3 squared plus 2 as shown here in figure 2.2. So notice that if this is the graph of y equals x squared, we know that 2 units up and 3 units to the left will give us the graph of this function over here, y equals x plus 3 squared plus 2. Notice that this will give us then the vertex or the coordinates of the vertex of the equation, because it's going to be minus 3, comma 2, which are the two numbers directly related to this here and this. Now we're going to take a look at completing the square. So notice that if you have a quadratic expression such as x squared plus px plus p half squared, this is going to be the square of the binomial x plus p halves. Now you can convince yourself that this is true by expanding x plus p half squared. Now to complete the square, we add a constant to a quadratic expression to make it the square of a binomial. This is going to be much clearer in the example that follows. So here we are with example 2.1. And it says, find the equation of the axis of symmetry and the coordinates of the vertex of the graph of f of x equals x squared minus 8x plus 18 by rewriting the function in the form f of x equals a times x minus h squared plus k. So notice that if we have x squared minus 8x plus 18, recall from the previous slide, we had that the functions in the form x squared, or the quadratic functions in this form, x squared plus px plus p halves squared, are the expansion of the binomial x plus p halves squared. In other words, notice that if I grab minus 8, divide that by 2, and square it, I'm taking this value here. This would be p. This is going to equal negative 4 squared, which is 16. That means that if I rewrite this as x squared minus 8x plus 16, this will be a perfect square, or the square of a binomial. Now notice that I still have to write 18, so I need plus 2 here, right? 16 plus 2 is 18. So I'm not really changing anything in this equation. I'm just separating 16 from 2 in order to be able to write this as a perfect square. So notice that this is the same as x minus 4 squared plus 2. And then we say that f of x is equal to this. So this is the vertex form of this function here, right? This is the vertex form. Now the vertex is going to tell us what the equation of the axis of symmetry. I have that the coordinates are going to be 4, 2. This is the coordinate of the vertex. So this is the vertex. Why positive 4? Well, remember that here the transformations are backwards, right? So minus 4 means 4 to the right, and then this means 2 up. So once we have the coordinates of the vertex, we also know what the equation for the axis of symmetry is. It's going to be simply x equals 4. So what does this mean in a graph? Well, if we have a graph, we would count 1, 2, 3, 4, and then 1, 2 up. And right here would be the vertex of the parabola. And the axis of symmetry would be the line x equals 4. So now let's continue with example 2.2. And it says for the function g such that x maps, now notice that this is terminology for functions, right? X maps into minus 2x squared minus 12x plus 7. Part A, find the axis of symmetry and the coordinates of the vertex of the graph of g. So this is exactly the same as the previous example. The only thing is that here we have a difficulty, and it's this negative 2 that is multiplying x squared. In order for us to be able to do the completing the square procedure, we will need to factor out this negative 2 since I need the coefficient of x squared to be 1. Notice that we can rewrite this as negative 2 times x squared plus 6x minus 7 halves. And then now I can complete the square of this part that is inside the parenthesis. Remember that the third term for the trinomial to be the expansion of the perfect square will have to be 6 halves squared, which is going to be 3 squared, or 9. So I will rewrite this as being equal to minus 2. And then here I'm going to write x squared. Notice that I'm going to say x squared plus 6x plus 9. So this is a perfect square right here. But I can't just add 9 out of the blue. I will have to subtract that as well. So minus 9 minus 7 halves. And then notice that this part here is going to be equal to minus 25 halves, right? This would be minus 9 minus 7 halves is minus 25 halves. So if I multiply everything by negative 2, I'm going to get minus 2 times, and this is already a perfect square, so x plus 3 squared, and then plus 25. That's the result of multiplying negative 2 times negative 25 halves. So notice that I have the information that I needed to solve part A, because the axis of symmetry is going to be the function or the line x equals negative 3. So that's the axis of symmetry, and then the coordinates of the vertex are going to be, so the vertex is going to be minus 3, comma 25. So now for part B, they want us to indicate the transformations that can be applied to y equals x squared to obtain the graph of G. So remember that we said that G is such that x maps into the function minus 2 times x plus 3 squared plus 25. So what are the transformations that can be applied to y equals x squared to obtain this? So notice how we could say 1, translation, 3 units left. And we know that from here. For 2, we could say vertical stretch by a factor of 2. And that's from this multiplication, right? 2 times this. Then, because the 2 has a minus in front, we could say reflection across, in this case, it would be the x-axis. And finally, we could say translation 25 units up. And that's from this. And then finally, for part C, it says find the minimum or the maximum value. Now remember that the concavity of a function depends on whether a is less than or greater than 0. So a refers to this first value here. Notice that this is negative 2. That means that the parabola is concave downwards. Therefore, the vertex would indicate a maximum. And then since the vertex is minus 3, comma 25, then the maximum for this function, the maximum value, would be y equals 25, which is this here. So now we are going to talk about zeros of a quadratic function. A specific value of x is a zero of a quadratic function f of x equals ax squared plus bx plus c if it is a solution, also known as root, to the equation ax squared plus bx plus c equals 0. The x-coordinate of any point or points where f crosses the x-axis, therefore the y-coordinate is 0, is a real zero of the function. So notice that here we have 3 different possibilities for the zeros of a quadratic function. You can have a case where there are 2 real zeros, and that means that the parabola crosses the x-axis in 2 different places. It can have only 1 real zero, which means that it is tangent to the x-axis. This is also known as having 1 double zero. And then finally, there's a case when there are no real zeros, and that means that the parabola does not touch or cross the x-axis. So now we have the quadratic formula and the discriminant. So let's recall that the quadratic formula is the formula that can solve ax squared plus bx plus c equals 0. And what it says is that the solutions to this equation are going to be x equals minus b plus minus the square root of b squared minus 4ac divided by 2 times a. The expression beneath the radical, so this expression right here, beneath the radical, b squared minus 4ac, tells us whether the zeros of a quadratic function are real or not real, also known as imaginary, because it acts to discriminate between the types of zeros. B squared minus 4ac is called the discriminant. It is often labeled with the Greek letter delta, uppercase delta. The value of the discriminant can also indicate if the zeros are equal and if they are rational. Okay, what this means is this. Notice that because this is inside a square root, if it's negative, it has no solution. So if this is negative, if the discriminant is negative or less than 0, then we would say no solutions, no real solutions, because it would have something else called imaginary solutions. If the discriminant, b squared minus 4ac, is equal to 0, then the equation has one real solution. And finally, if the discriminant is greater than 0, then it would have two solutions, right? And don't forget that these are real solutions. So let's continue with example 2.4, and it says use the discriminant to determine how many real roots, so these are real roots, each equation has. Confirm the result by graphing the corresponding quadratic function for each equation on your GDC. So let's recall that the discriminant is going to equal b squared minus 4ac. So for letter A, we have that it would be 5 squared minus 4 times 2 times minus 3. And this is going to be 49, which is greater than 0. Therefore, the equation for letter A should have two real roots. We're going to confirm that by using the GDC. So what you have to do is go to this part where it says y equals, top left corner, y equals, and then you plug in the function. Notice that you go to x squared plus 5x minus 3. And then top right corner, click graph. And there you have it. You can see that there are two real solutions because the function crosses the x-axis in two different places. Okay, so now let's do B. So for B, the discriminant would be minus 12 squared minus 4 times 4 times 9. And if you do the math, this is equal to 0. Now this means that there's only one solution, one real solution. And we're going to verify this with the GDC. So what we do is that we go back to where it says y equals, and let's clear that first equation. So we're going to write 4x squared minus 12x plus 9. And we hit graph. And there you have it. Notice that this particular graph intersects the x-axis. Actually, it's tangent to the x-axis at one single point. Therefore, it has one real solution. And then for C, we would have that the discriminant is going to be minus 5 squared minus 4 times 2 times 6. And if you do the math, this is going to equal negative 23, which is less than 0. Therefore, this equation for letter C has 0 real solutions. Now let's verify it with the GDC. So again, we go to y equals. We can clear that one or just leave it there. And let's type in 2x squared minus 5x plus 6 and hit graph. Well, it's just above the other one, so I'm going to delete the first one, clear it out, so we have a better picture. So graph, and notice that this second equation does not cross the x-axis, and therefore it means that it has no real roots. So let's continue with example 2.5. And it says, for 4x squared plus 4kx plus 9 equals 0, determine the value or values of k so that the equation has A, one real zero, B, two distinct real zeros, and C, no real zeros. Okay, so if for A, we want this equation to have one real zero, then the discriminant has to be equal to 0. Therefore, b squared minus 4ac must equal 0. So notice that this is going to be 4k squared, right? That's going to be b, 4k, right here, minus 4 times a, which is 4, times c, which is 9. So notice that this has to equal 0. And then we're going to get 16k squared minus, and I'm going to use this here, which is 16 times 9 should equal 0. But then I can cancel out this and this, and I end up with k squared minus 9 equals 0. Therefore, k squared equals 9, and then k can equal plus minus 3. So that means that k can either be positive 3 or negative 3, and we're going to get that the equation will have one real zero. Now for b, we want two distinct zeros. So that means that this same expression here, k squared minus 9, should be greater than 0 because this is the discriminant, right? So k squared minus 9 should be greater than 0. In other words, k plus 3 times k minus 3 should be greater than 0. And that means that we have critical values that are minus 3 and 3. And based on that, we can draw a table through which we can find out which values will give me a negative result or a positive result. So this is negative infinity, and this is positive infinity. Let's test a value that is less than negative 3. So if I plug in negative 4 here, I'm going to get a negative. If I plug in negative 4, I'm going to get a negative. Negative times negative is positive. If you plug in a value between negative 3 and 3, any of the values between negative 3 and 3, let's say 0, you're going to get negative. And if you plug in something greater than 3, you're going to get positive. So that means that you're going to get two distinct real zeros for values of k that are less than negative 3 or values of k that are greater than 3. And that means that we have the solution for letter C, because this area here is where it's going to be negative. The equation is going to be negative. Therefore, there will be no real zeros when k is between -3 and 3. Okay, so now we're going to talk about another form of the parabola or the quadratic equation or function. And it is this one right here, f of x equals a times x minus p times x minus q. So this would be the result of the factorization of a function in the normal or standard form for the quadratic function. The advantage of this form is that we can easily identify the x-intercepts of the graph of f. So notice that if we have the quadratic function in this form, we know that it's going to intersect the x-axis at the points p, 0 and q, 0. So like I said, we would need to factorize in order to rewrite a quadratic function in the form of ax squared plus bx plus c to this other form, a times x minus p times x minus q. So that's why this is also referred to as the factorized form of a quadratic function. Since a parabola is symmetric, then the x-intercepts p, 0 and q, 0 will be equidistant from the axis of symmetry. You can see that in figure 2.6. Notice that here to the right we have p, 0 and then q, 0 to the left, and the axis of symmetry is right between those 2 points. Therefore, that is going to equal the average of those 2 points. Notice that x is equal to p plus q divided by 2. Now the other thing is that the vertex will also be given by the x-coordinate. Since the x-coordinate is the same as the axis of symmetry, it's going to be p plus q divided by 2. And then the y-coordinate of the vertex would be the result of plugging that into the function. That's why it says f of p plus q divided by 2. So now let's take a look at example 2.6. And it says, find the equation of each quadratic function from the graph in the form f of x equals a times x minus p times x minus q, and also in the other form, right, the standard form. So let's take a look at a. F of x is going to be of the form a times x minus p. So notice that x minus 3 for p, right, grabbing this root or 0, times x minus 1. Therefore, this is equal to a times x plus 3 times x minus 1. So all we need to do now is find the value of a. But to do that, we can use this point here, the y-intercept. Notice that the y-intercept for this graph is 0, 6. So that means that when f of x is equal to 6, x is equal to 0. So 6 equals a times 0 plus 3 times 0 minus 1. And from here, we're going to get that 6 is equal to negative 3a. Therefore, a is equal to negative 2. And now we have the function. It's going to be f of x is equal to negative 2 times x plus 3 times x minus 1. And then the standard form would simply be the result of expanding this and multiplying by negative 2. So when you do that, you're going to get minus 2x squared minus 4x plus 6. So now we have b, but notice that with b, we only have one solution or one root. So that means that the function is of the form f of x is equal to a times x minus 2 squared. So that's when we have one double solution. And then to find a, let's use the fact that the y-intercept is 0, 12, as we can see on the graph. 0, 12 is the y-intercept. Therefore, when f of x is 12, we have that x is 0. So a times 0 minus 2 squared. And then from here, we're going to get 12 is equal to 4a. Therefore, a is equal to 3. And then finally, we have then that the function is f of x equals 3 times x minus 2 squared. And for the standard form, all we have to do is expand this, and we're going to get f of x is equal to 3x squared minus 12x plus 12. So we end this video with example 2.7, and it says the graph of a quadratic function intersects the x-axis at points -6, 0 and -2, 0, and also passes through the point 2, 16. Part A, write the function in the form f of x equals a times x minus p times x minus q. Okay, so this is very similar to the previous exercise, and we know that f of x should equal a times x plus 6 times x plus 2. And then we can use the fact that they give us a point, which is 2, 16, to find the value of a. So we would say 16 is equal to a times 2 plus 6 times 2 plus 2. And then we're going to get that 16 is equal to 32a. Therefore, a is 1/2. And then we have that f of x will equal 1/2 x plus 6 times x plus 2. For b, they want us to find the coordinates of the vertex of the parabola. Now let's remember that the x-coordinate of the vertex of a parabola is the axis of symmetry. And we know that that's going to be given by the average of the roots, or 0. So x is equal to -6 plus -2 divided by 2. And from here we get -4. So this would be the axis of symmetry, but also the x-coordinate of the vertex. To find the y-coordinate of the vertex, we plug this into the function. So f of -4, which is going to be 1/2 times -4 plus 6 times -4 plus 2. And then if we do the math here, we're going to get that this equals -2. Therefore, the vertex is going to be -4, -2. And then finally it says, write the function in the vertex form. This is the vertex form of the quadratic function. And we have all we need, right? We have f of x is equal to a. We know that a is 1/2, so we write 1/2. And then remember that it's x minus h, but h is -4, so we're going to have x plus 4 squared -2. So this would be the vertex form of the parabola.